about, the next thing is to think about the functions which are vector valued. Okay? Shall I first prove, for example, a theorem? Quickly a theorem for a scalar valued functions that if the linear approximation, a good linear approximation exists for a function, it must be unique. In other words, roughly, if the derivative of the function exists, it must be unique. You can't have two derivatives of the function. So let's think over, let's ponder over it actually. So this is analog to, saying in the one dimension, for a unique slope. So on a curve, okay, if you choose a point, there will be only one line, okay, that has slope equal to the derivative of the function. That would be the tangent line. You can't have more than two lines actually whose slope is derivative. Okay. So it's going to be only one line. So maybe the analog is going to be here. So in other words, if good approximation exists, by good approximation, whenever I will say good approximation, now the good doesn't have an English meaning actually, so it has a technical meaning. Okay. So good is not just Angrezi wala good, it has really, how do you call, technical. Good approximation to f at a if exists, then it's unique. Okay, then it must be. You can't have two good approximation for a single function at a point actually. Okay? And the proof goes like this. So how do you prove the uniqueness theorems actually? So if you have to prove uniqueness of something, have you learned something in linear algebra or maybe somewhere where you want to prove something unique, and what do you do? Either you can do contradiction, okay? That imagine you have two different things are maybe good approximations, and that would take you the contradiction. Or you say that, okay, if a function has two different good approximation, those both must be same actually. Okay? So suppose L of h and L tilde of h be good approximations. Good approximations of f at a. This is what. So what does this mean? This means that if I compute f of a plus h minus f of a, okay, then I'm going to have good approximation plus error, but the error depends on f and approximation and the point A in the h actually. Okay? But since L tilde of h is also a good approximation to, what do you say, f at A, so this must also be equal to L tilde of h plus E f L tilde A h. This is just applying the definition. Just applying the definition. Okay? So what follows from here? So what follows from here is that you have L tilde of h plus E f L tilde A h plus E equal to L of h plus E f L and h actually. Okay, so this equality you're gonna have it. And what you can already intuitively observe actually. Okay? You can intuitively observe, okay, and this is true for all h. So this equality is true for all H in Rn. So what do you wish to basically have? Okay, so you want some magic to happen in such a way that if I take a limit, this should go to 0 and this should go to 0, so that you can have, the equality of the both actually. So that's what you would like to have. Okay. Now, if this is what? So if H is a vector, so how can I have it actually? So I know that H is a vector in Rn. So I know every vector can be represented as some magnitude multiplied a unit vector actually. Okay? So if H is a vector in Rn, so it must be also something like that. You have a magnitude of it multiplied by the unit vector corresponding to it. Okay? You know that? Simple. Take it. So what do you do? Now in this equation, divide throughout by t. So if you're going to divide throughout by t, what you're going to get? L of H by t. So L is a linear kind of a map actually. So you can insert t inside of it. Okay. So what you're going to get? L H by t, right? So I'm saying divide both sides by t. So dividing this guy by t, so L is something linear. So if something is linear, then you can take the number inside the argument. Okay. So I can do it. So if I'll have it, I'm going to have H over t, but the H over t is u. So I can write this is L of the unit vector u plus the error as divided by t, AH equal to, you're going to have L tilde of u hat plus the error f L tilde divided by t. Okay? And I'm saying that take t goes to 0. Take t goes to 0. Are you getting the point? So if I will take t goes to 0, so there is no t here, so you're going to have L of u tilde. So what do I know about the error? Okay, so this is the error, and t is what? T is the magnitude of the H actually, isn't it? So if I am taking t goes to 0, I am actually saying that magnitude of H goes to 0. So if the magnitude of H goes to 0, this guy goes to 0. And if the magnitude of H goes to 0, this also guy goes to 0 as norm of as norm of H goes to 0, right? So what is remaining now? If this guy L of u hat equal to L tilde of u hat. Okay? So I want their equality on H. So what should I do? Multiply both sides by t. So if I multiply this by t and this by t again, so what you're going to get? So I can bring t inside, I'm going to have L of H and L tilde of H actually.
यहाँ पे magnitude of H upward to 0, इसका ये किसे कह सकते हैं? जब error भी 0 वापस
नहीं, इसलिए कह सकते हैं because if I take the magnitude of H, I'm going to get the magnitude of u tilde, and that is equal to t, right? बाकी रही बात, why the error would go to 0? Because I have assumed that this is a good approximation. If it is a good approximation, by definition, the error divided by the norm of H goes to 0. So the both would go to 0. Okay. So that's why this shows that when I'm taking t goes to 0, I'm basically saying that norm of H goes to 0. Okay. That's it. So what does this shows? That if you have two linear approximations, good approximations to a function at a point, they can't be different, and hence if the function is differentiable, the derivative must be unique. So you can't have two derivatives actually for a function. ठीक है? समझ आ रही है बात थोड़ी थोड़ी सी? Now I would like to move the next part, and the next part is how to compute the derivative for a vector valued function actually. Okay? For a vector valued function.
अगर एरर समथिंग हो तो क्या हम प्रेशर डेरिवेटिव कैलकुलेट कर सकते हैं? अगर एरर समथिंग हो
So, I mean, the derivative can only be computed if the error goes faster than the norm of h goes to 0. Okay? In other words, this ratio, error divided by the norm of h goes to 0 as norm of h goes to 0. Then you can have that function as differential.
अगर एरर समथिंग हो तो हम क्या कर सकते हैं कि प्रेशर डेरिवेटिव ज्यादा लेंगे?
I mean, if error can be something. For example, in our previous example, error was h1, h2, so it's something. But we don't have problems with error being something. We have to think that, okay, whatever this something is, if you divide it by the norm of h, that must go to 0 h. Okay. So the next important thing is to do what? Is to define, the derivative of the vector valued function. Okay, and intuitively, I yesterday talked about it. The last time I talked about it, that if you have a vector valued function like the continuity or maybe the limit, okay, what we can guess to have is that if a function is if the each function, if the each component of the vector valued function is differentiable in this sense, then the vector function is differentiable. So let me define abstractly and then prove this result, that if you want to differentiate a vector valued function, just do what? You just differentiate every component and make a vector out of it, and that will be the derivative of the vector valued function. Okay? So suppose f is a map from U to Rm now, where U is open in Rm. Okay? So we say f is differentiable at a point A in the domain U if I can find, what is your guess? So here the good approximation was mapped from Rn to R actually. So if we can find a good approximation, okay, approximation L from Rn to Rm, okay, such that what happens, that if you compute the error of the function, okay, corresponding, so error between the function and the good approximation or the approximation that depends on A and H, okay, and divided by the norm of H, and that goes to 0 as what? Norm of H goes to 0, okay. So if this happens, then you're going to say that f is differentiable at a point A, where I must say that EF, so error between the function and the linear approximation that depends on A and H is basically what? So it's f of A plus H minus f of A minus the linear approximation. So that gives you the difference between the increment, okay, the change in f and the linear and its linear approximation. So that's what is error. So in other words, I'm saying that this error should go to 0, but more faster than the norm of H goes to 0. Okay, that's what it is. So you're going to say, okay, so what's the difference between the definition that you have there and here? So there's a crucial definition actually. Now your function is vector valued. So now I would like to talk explicitly about this object. But you can see that the same previous definition is motivating us to define things in this manner actually, and we'll see that this will work.
सर यहाँ पे आपने कहा कि अगर एरर समथिंग होगा तो उससे हमें मसला नहीं है सर अगर एरर समथिंग होगा तो वो एक अप्रोक्सीमेशन गुड थोड़ी होगी सर जैसे
गुड तब होगी कि when you divide it by the norm of h then goes to 0. In other words, the error goes to 0 more faster than the norm of h goes to 0. Otherwise it's just approximation actually. So it's just error, it's just taking the difference. Okay? So this approximation is a good approximation if the difference between the increment and your potential approximation is what this error, and this error goes to 0 more rapidly than the norm of h goes to 0. That's what this is the definition.
I think error approach 0 vector.
No, obviously, so at the moment I have written it abstractly, so there are many things hidden here. So now I'll get into, the real, beast that is sitting inside it actually. So let's get into the, what do you call, the devil's hidden details. So let's get into the details and see how does all this looks. So now I would like to remark something important. You have to keep one thing in head. This is the error between increment and approximation, not linear approximation. Not every linear approximation is a good linear approximation. If this error additionally satisfies this, then you're going to say that your approximation is a good approximation, and hence I must also say that basically the derivative of the function a would be this L actually. So in other words, the derivative that you want for the function at a is this L. Okay? So that's abstract definition, so let's get a bit more concrete. So when I'm saying that f is a map from Rn to R, the f should look like this. So f1, f2 and fm. Okay? So that's how it should look like. Where each of this fi is a map from Rn to R. Right? So it's a map from Rn to R. So a scalar-valued actually, where I is 1, 2 and up to. Is it making sense? The question is, how does the L of h would look like? I'm going to say, I'm going to say the L of h. Now since each one of, one thing that would be, so what I want to do, I want to find an approximation, a linear approximation for this f around a actually. Okay? So if you want to do it, how can I do it? So what can I do? Using our previous analysis, I can try to find a linear approximation for each of these components. And then using those linear approximation, I can make a linear approximation for the vector actually. So I'm defining L of h to be the linear approximation that I have obtained how? By computing the linear approximation of each of these functions actually. Okay? Where I say where Li of h is Li is a map, each of it is a map from Rn to R, and approximations. At the moment I'm not saying they're good approximations, I'm saying approximations, linear approximations to what? To Fi. Right? Okay. Now, when this linear approximation would be a good linear approximation. So if it is a linear approximation, what identity it must satisfy? So the obviously identity that it must satisfy is fi of a plus h minus fi of a equal to li of h plus error between the function li and the linear approximation that depends on a and h. Right? So this must be true for all I equal to 1, 2, and n, because that's what is that's what is the definition of the linear approximation of the error. Okay. Now what I would like to do, I want this linear approximation to be good. So what additional condition should it satisfy? So the additional condition should it satisfy? Now this, each of this li is good if what happens? Li of h, the error of fi and li depending ah should go to the 0 as norm of h goes to 0, right? Norm of h goes to 0. Now, what would be, so what I did, I took f, for each component, I had an approximation, a linear approximation, and using these linear approximation, I created a linear approximating vector for the original function hl. Now what I need to do, I need to make the error function for this original function. So what would be the error? What thing is going to play the role of the error for this original function? Okay. So what you can do is that take all these errors and make a vector out of it. Okay. So see, so what I'm trying to do is to theoretically justify everything, okay? So that theory should make sense to you. Okay. Now, let me define the error function for okay, f and l depending on a to f and t. So it should be what? That take each component of f and take its linear, so ef1 l1 up to efm lm. So that is going to be the error function. Now let me know when this error function or when this L for the original function is a good approximation. Now I can say that this L, which is a map from Rn to Rm, I can treat this as like that, is good approximation for what? For by definition for f at a, if and only if limit norm of h goes to 0, the error fl ah divided by the norm of h goes to 0, right? That's what is the definition. Okay? Of what? Of L being a good linear approximation, right? Now the question is, I have this vector which I know, and I want to divide it by the norm of h and want to take it to 0. So what would be this expression if I compute explicitly? So it's gonna be take each component f1 l1, okay, or if and only if. So I have this vector and divide by the number. So this means that I have to divide norm of h by each number. So I would say this goes to 0 It means that if and only if each component goes to 0 actually. So if and only if E, F, I, L, I of AH divided by norm of H goes to 0, right? As norm of H goes to 0. Is it making sense? So what does this mean? So I would like to summarize this now. So the summary. I don't know why the heck these don't work actually. Which would work. Therefore I don't like using these whiteboards. Summary. So can I, by combining all these, summary is this: L is good approximation of F at A if and only if each of Li is good approximation at of F of Fi. Okay? Is this making sense? So what does this mean? This means that if you want to find L, then try to find Li for each Fi, okay, and make a vector out of it. And that would be, the derivative that you want. So in other words, if you want to compute, say, hence, in a nutshell, I can say, doesn't work. Not to use whiteboard. Okay. So see, you have to make yourself comfortable that why things are working the way. So you don't have to just take things on my word. Like you have to justify it. In other words, when I was saying that if you want to compute the Fréchet derivative of a vector valued function, then just compute the Fréchet derivative of each component and make a vector out of it. So the question is why this works actually. Why computing the Fréchet derivative of each component and making vector out of it is going to give you the Fréchet derivative for the vector valued function? The answer is this is justification actually. Okay? So the good linear approximation for vector valued function is going to be good. A linear approximation of the vector valued function is going to be good if each component has a good linear approximation. Okay? So this is the case, and hence I can say that, in other words, if I want to find L, I just need to find this L1, L2, and Ln, where each of this is linear transformation, right? And L is a linear transformation of the linear transformation, okay? And what? And if you want to compute the df of A, where f is a map from Rn to Rm, what you just need to do is compute the Fréchet derivative of each component, okay? And of each component and make a vector out of it. Actually, so must write M here. Okay? So that's the theoretical justification. So now whenever you use this formula, you know why this is true. Okay? So we proved this proposition actually.
तो यहाँ पे जब हम L की वो कंपोनेंट वाइज हम लीनियर एप्रोक्सीमेशन फाइंड कर रहे हैं, सर यहाँ पे हम एरर वो कहाँ जाएगा, उसके लिए भी करना पड़ेगा।
ये किया है ना। So what we said for each fi I can find what for each fi the vector valued function, I can find a linear approximation. Okay, so that's a linear approximation. And out of these linear approximations, I can make a linear approximation for the entire function. Okay, Rn to Rn. Now, each of this linear approximation is good, so that's what I have showed here. Okay, if the error corresponding to each function, in other words, this error, this is something that we said, that the error corresponding to the